Thank you so much. Okay, let me make sure that this is working. Okay. No, was working before. Huh? Okay. Okay. Then, before I start talking and say anything, okay, let's use this. This talk is mainly based on my collaboration with many people. I will mention mainly things that I did with Mark Weiss from Caltech, um, Clara Murgi, that is my student that now will be a junior staff member as Sir John Butterwood, which is actually an experimental person. And two of my graduate students are working now, and actually most of the work are based on my collaboration with them. Um, and basically what I will do, I will try to give you a feeling what I have been doing this year. These are the publication. Of course, I will not go through all the details, but I want to give you a feeling what I've been doing this year. In particular, the first paper, I'm very happy that I managed to do this year. At least in the US, you always have to make a joke in a talk. I don't know here. But you see, these are the four papers I published this year, and I am not allowed to publish more because the Congress passed the Inflation Act, and I cannot overproduce. Okay? Sorry, that was a joke. Okay? Then I don't supposed to publish more than that. Now, before I start and tell you about the main idea, I want to make a few comments. Uh, Basically, for a long time, for a long time, we have been thinking about dark matter. And one of the most popular class of candidates are called WINS, right? Most of you know the name. In particular, the one that called more the attention in the community was actually neutralino dark matter for a long time. And we were very optimistic about supersymmetry. I believe still we should be in a different way, but we should be. But you know, in SUSY, when you write the supersymmetry extension of the standard model, to be able to get the dark matter candidate, you have to actually to put by hand a symmetry that we call matter parity or R parity. I use matter parity because if you work in superfield, matter parity is -1 for any matter superfield and +1 for the rest. If you actually impose this symmetry by hand, the lightest supersymmetric particle, in this case a neutralino, can actually be a good dark matter candidate, and people work for that for more than 40 years, maybe. I don't remember exactly, but early 90s. This has been very exciting. And today, since we don't see supersymmetric collider, it's a little bit hard to, but you know, it's just one possibility in a different way. However, I personally spend a lot of time thinking about the origin of this symmetry because you are putting by hand, and this is the one that allow you to get dark matter. If you really try to understand how do you get a mechanism to justify this symmetry, you have to go to any theory where B minus L is inside the algebra, and you will be surprised, and most of the time you will get R parity conservation, R parity violation, but there is no proton decay, okay? Uh, but you know, this was popular for a long time, and we don't know, maybe we will have a surprise. Huh? The other class of candidate, I think I will go old fashioned because I don't want to waste time on this. The other kind of candidate that has been in the field for a long time is the QCD action. I mean, QCD action is the most motivated candidate. And it's because, you know, it's in the same way. You want to have a solution to the strong CP problem, and you find, Wilczek and Weinberg found that this guy can be a dark matter candidate. And this has been, you know, very popular in the field. If you want to write the scenarios where you can compute all the coupling in the QC action, you have to use type of KS, whatever, the dying Kima mechanism or dye mechanism, and you are able to, you know, to understand all the property of the QCD action. However, here, as you notice, the Pichy Queen scale, they're very strong bounds. And if you're really serious about the stability of this and testing the mechanism of what is happening, you have to go to the high scale. Okay? Again, these two examples have been there for a long time. And this always has been well motivated because people wrote a theory thinking about one particular problem, and as a bonus, you get a prediction that you could have a dark matter candidate. And this is why most of the people like these ideas and still we like these ideas, okay? However, I just want to mention a paper that I don't have time to talk, but actually you can find well protected, if you think about the quality problem, for the strong CP problem using Nelson bar mechanism in gauge symmetry, and they actually work very well. You don't need a QCD action. No? But in this talk, I will actually follow that philosophy. Okay? The philosophy is, you write a theory for whatever you want, whatever problem you want to think about, and as a prediction, you realize that you can have a dark matter candidate. Okay? This is what happened in supersymmetry. In supersymmetry, it's true that you have to put by hand the symmetry, are parity violating couplings, but they are protected by B minus L, then it's actually not really argument. It's just you didn't want fast proton decay, but this is the matter of everything can be consistent. But this is the reason why we like, apart from all the beautiful things about supersymmetry, is that, you can have a dark matter candidate even if you were thinking about whatever other problem, the Higgs mass or whatever. And the action is the same philosophy, right? Then I will follow that philosophy. I want to show you a couple of examples where you get a dark matter candidate and you were not expecting that. Okay? You didn't think about dark matter. And I call that a prediction, a bonus, or whatever you want to call, okay? A gift. It's like you go to the supermarket, you buy an aspirin, and the lady there gives you a candy, You didn't expect that. Maybe the candy is good, maybe it's not good. Okay? And the first thing is that there is here interesting relation with neutrino masses and dark matter. What I mean by that is that, neutrinos are massive. Okay? And you have to think about them because the standard model doesn't provide the explanation for them. And neutrinos, they can be Majorana or Dirac, we don't know. We know that the masses are very tiny, below the 0.1 eV scale, way below any fermion masses. The standard model doesn't provide the mechanism. You have to think about neutrino masses. There is no excuse. Okay, this is a really well-defined problem. Okay, but we don't know even if it's Majorana or Dirac. Okay, and then you have to try different possibility. Since I am in Italy and Majorana was Italian, I would think about Majorana. And then, if you look at Majorana mechanism to get Majorana masses, there is a huge list of this. From the well-known type 1 CISO mechanism to the Witten model that the Fino community doesn't know, but it's one of the most beautiful papers you can read. And at the same time, we have many theories like Patti-Salan, grand unified theories, all these things. These theories, typically, they have, you can write, let's say, a SO10 or Patti-Salan theory, and you will see the neutrinos that have to be Majorana, but the scale has to be high scale, close to the grand unified scale. The canonical CISO scale is 10 to the 14 GeV. And then, these ideas are appealing, but most of the time in these models, the scale has to be very, very high. Then if you think about the stability of the mechanism for neutrino mass, it's really hard to imagine that we can do the same thing that we do in the Higgs, that you can produce, look at the decays, the production cross-section, and measure the properties, okay? But again, there is no excuse here. You have to think about neutrino masses, okay? Whatever mechanism you like, and these type of ideas using grand unified theories has been there for a long time. And this you can call kind of a standard paradigm for neutrino masses. And here I will show you one example that is totally different. And as I told you before here, and you know very well, in the standard model, we don't know if neutrinos are Majorana fermions or Dirac, but it's a key symmetry that is total lepton number. If it's broken in 2 units, you get Majorana fermions. If he is conserved or is broken by any unix, you can never write the effective operator when delta L equal 2 is Dirac. The electron number is accidental global symmetry in the standard model broken by SO2 instantons. It's normally free. And then if you want to do what we did here is that you want to write a theory for neutrino masses, and the key symmetry is just electron number, total electron number, okay? But now you want to make that symmetry local, okay? B minus L is very easy to gauge, but doesn't really tell you anything about it, what kind of neutrino you will get, and never will make any other prediction. You never can know what the scale is. If you just try electron number, try to gauge, the first thing is that it's not anomaly free. And then you have to cancel these anomalies in the same way how we cancel anomaly in the standard model. And as a result, I will show you, you will get a dark matter candidate. And when you put the cosmological constraints, if you are thinking about Majorana neutrinos, you realize that the Ciso scale has to be low. Then there is a good chance to test the mechanism for neutrino mass. But as a gift, you are getting a dark matter candidate. And this is the main idea of the first part. Now let's see how that works. Because when I say you have to write the theory, there, you have to put some high standard. The theory has to be simple. You should make good predictions. You should not make a mess in cosmology. And you should be able to generate masses for everybody in a simple way. It should be a simple thing, okay? No messy stuff. Now, the first thing you have to do, you have to check all the anomalies, right? Then, you take the standard model leptons. I am not writing color because they're leptons. And you check all the anomalies. You can see the SO2 anomaly is not zero, and a couple of others are not zero. And then you have to think about that and see exactly how you do in the standard model. Remember that in the standard model, we cancel by generation all the anomalies. If you remove any degree of freedom on the standard model, you cannot cancel anomaly, okay? Then spontaneous symmetry breaking doesn't make any sense because gauge invariance is gone even before you even think about. Here they say, okay, these are all the anomalies, and then maybe it looks pretty hard maybe to cancel all of them and get a good looking theory that could make any prediction. Okay, then there are many solutions that we proposed during several years. As I said, for my surprise, I found the simplest possible thing you can do. This is why I keep thinking about this topic. And I will show you two examples. One is this theory looks very similar to the standard model. When I think about the quantum numbers of the new fermions needed for anomaly cancellation, and I will show you what I mean by minima. Minima means is that you look for the minimum degree of freedoms that allow you to cancel all the anomaly and see if you get a prediction. The nice thing is that doesn't matter what solution you use, you always get a dark matter candidate there. And this is, nice because it's one of the reasons why we like a SUSI, the QCD action. You try to do something and you get a prediction, okay? And of course, you have to check that you are in agreement with the experiments and everything, and you don't make a mess, okay? Then the first thing that I will show you is the model that is no minimal, okay? It's no minimal. This is no minimal. However, the notation maybe can confuse you, but these are Bertholli leptons, okay? These are the same quantum number of the standard model leptons. 1, 2, minus 1/2, the something with electric charge minus, like, let's say, heavy electron. And these two guys that are neutral here, okay? Then again, it's not a minimal. You just put Bertholli. When I say Bertholli with respect to the standard model, Bertholli leptons, you cancel all the anomalies. The anomalies are canceled when L1 minus L2 is -3. This is the only condition anomaly cancellation gives. If you want Majorana dark matter, doesn't matter. You have freedom to choose the value of L1, L2. The difference has to be -3. I will show you the case of Majorana dark matter, but again, doesn't matter. Chi-L and Chi-R, any combination of them, you can see that it's stable, it's neutral, and it's a dark matter candidate. Again, Also, you don't put the stability here by hand, okay? We are coming now, we are coming. Right, that you put something, you have to say how they get mass. Today, nobody can get mass for the standard model Higgs because you will destroy the standard model Higgs property. Okay, then you have to have a mechanism, a simple mechanism to give mass to this. This is actually true for any station of the standard model. Chiral, you see, they're chiral. They're like our leptons in pairs, but they have different lepton number. Look at that. They're like exactly. This is like a fourth generation leptons, but you have the Bertholli pairs, right? But the L1, L2, the only thing the anomaly cancellation constraints is the difference. Okay, we'll see now. No, they cannot because you will destroy the Higgs property. No, if you oh no, it's chiral. They're chiral. Chi L, chi R. Look at that. But then if imagine you want to cancel the SO2 square lepton left, you want lepton number. You need something that is a SO2, right? By the way, if you take this actually is in the early paper, you take just one chiral extra family, you can cancel all the anomalies, but you destroy the standard model properties. That's why you need the Bertholli. But I'm talking only about the with respect to the standard model, no Bertholli with respect to L. Okay? Okay. Basically, no. Basically, you can assign any L number that you want, okay? But if you want to check, any, okay, you have to cancel the new anomalies and you should know, you should not spoil the standard model anomaly cancellation. Number 2, right? Because if you know, doesn't make any sense what you're doing, right? And then the anomaly, the standard model anomaly cancellation is guaranteed because you have Bertholli fermions with respect to the standard model. This is already constraining what kind of representation you can put, right? Now, when you say, oh, I want this L1, you see that you have psi L, eta R, and chi R. They have the same L because they guarantee you to cancel the anomaly as you cancel it in the standard model for the L. Any U1L standard model gauge group. And the other is also doing the same anomaly cancellation in the same way. There are a set of anomalies that are canceled between each other. But the SO2 left square U1L is canceled by the 2 doublet that you have there. And this is why where the L1 minus L2 is coming. Okay, but I can be more explicit later because I want to make sure I keep going. Okay, now how they get mass? You guys were asking, no? They cannot get mass from the standard model Higgs. Okay, then you have to introduce a new Higgs that will give mass to them. But something very interesting here is that in the standard model, lepton number is broken by SO2 instantons in 3 units. Here, when you want to generate Bertholli masses, for this guy, the fact that L1 minus L2 is minus 3, this Higgs has a fixed lepton number. Cannot change that. If you want to be consistent with the experiment and give mass to them, because they have to be heavy, they're collider bonds, this S has to have lepton number 3. As you should be able to expect from the anomaly cancellation and the generation masses. And in the case I am writing down the L1 minus L2, also these Majorana mass terms are allowed. If you want to study any other case, as we did before, but I will not worry about that, only one mass term like chi R, a bar chi L, will be able to be there. But these Majoranas are. Now, as I said, I am in Italy, one Majorana neutrinos, you have the usual CISO term, giving mass to the right neutrino, 2 units. Okay? And then, again, this is not a minimal model. I just try to show you something that is very familiar to you. Okay? And at the end, but every time that you speculate, it's better to find the minimal number of things when you are speculating because it's called minimal speculation. Here, this is not minimal speculation. This is a standard model like, and you are able to cancel all the anomalies. Okay? Now, this is very important for neutrinos. You have the seesaw mechanism. The neutrino masses are suppressed by the random neutrino mass matrix. But in this theory, you can get the upper bound, the right-handed neutrino masses, because it's constrained by this ratio. This is the new gauge boson associated, the gauge coupling, and a perturbative coupling. You want to be in the perturbative regime. Okay? Then if I will prove to you that the symmetry-breaking scale has to be low, you are generating neutrino masses through the seesaw mechanism at the low scale, and then you have a hope to test the mechanism for neutrino masses, because you are not at the 10 to the 14 GeV anymore, okay? Or whatever value you have. Then you have to do Rayleigh density. Again, now chi-L and chi-R, after symmetry breaking, there is a C2 symmetry is protecting them, any of them. And I'm showing you a case of the Majorana chi-L plus the chi-L-C. What you have to do the use of Rayleigh density. You put all the decays, all the annihilation channels and so on. Notice there is something special here. There is a J there. This is a pseudo Goston boson. What happens is I have S has unit 3. When this guy get the BEV, it gives mass to the C prime associated to lepton number, and give mass to everybody, all the extra fermions, right? But if I want the seesaw mechanism, I have an extra Higgs with 2 units, giving neutrino masses, okay? But one is 3 units, 2 units. Still, if you write the potential, there is extra global symmetry, and you will get a Goston boson. But you are so lucky here. We actually call this guy the Majoron, thanks to, in honor to Majorana. And historically, that was done actually Max Planck by Gelmini and Roncadelli at the Max Planck Munich in '82. And this pseudo-Goston boson is actually very interesting. Okay, but this is pretty standard. You compute the Rayleigh density computing the freeze-out mechanism, nothing weird. I don't want to use anything that is controversial, okay? Nothing strange, very standard, okay? But the J is actually a pseudo-Goston boson that get mass by dimension 5 operators that is allowed. Typically, when you read paper about the Majoron, people break by hand the global lepton number or whatever. Everything is local here. And then what you do the standard thing, okay? You compute the Rayleigh density. By the way, you see many graphs there. In reality, there is only one BEV, one C prime, and everybody is getting mass from the same Higgs. Then it's like the standard model Higgs. Any Yukawa coupling can be written by, it's a function of the C prime mass and the gauge coupling, and the masses of these guys. Then there is nothing. Then the dark matter is a lightless guy, is neutral in the new sector, right? You have this guy and the other are heavy. Then everybody can decay to the dark matter and to the standard model. You don't make a mess in cosmology. Then everything's well defined, okay? Then you do the Rayleigh density calculation, and there is always a resonant region where the dark matter relates to leptons. Hard to imagine you have to live there, but yeah, it's allowed. And the rest, you have to be in a region. You can increase a little bit, but not too much, the gauge coupling if you want to be perturbative, because the Higgs has unit 3. Then, there is like a upper bound the gauge coupling as well. But you have to be in a region to be consistent with cosmology, means you don't want to overclose the universe. And the nice thing about that is that if you look there, the C prime mass, the C prime associated to lepton number, has to live below, say 10, 15 GeV, okay? I mean, you can push a little bit. Means the symmetry-breaking scale is at that scale. You don't have to be there. I just want to tell you this is like the upper bound. For neutrino people, this is more than welcome, because the seesaw scale is 10 to the 14 GeV. There is no way we can go there, okay? But here, everything is happening at the low scale. And then the question is, okay, everything is consistent, as I said. I started thinking about neutrino masses. I never even imagined to get any dark matter candidate. But there is a dark matter candidate cosmology tell me if you don't want to overclose the universe, the mechanism or the theory of the symmetry breaking where I am getting my neutrino mass, everything has to be low scale. Very good. What happens, these are the questions I was waiting for. You see, every time that people do simplify stuff, right? Models and whatever, you can always push all the way to unitary bound, whatever, right? What happens is that the dark matter is getting mass from the same symmetry breaking scale. That Yukawa has to be perturbative. Okay? Then anything basically, think about this chi. This Yukawa here has to be perturbative. But the point is that this BEF, there is an upper bound. Okay? And then for a given dark matter mass, you want this always to be perturbative. This is killing everything below this line here. Oh, you have to be in the line. Yeah, I am ultra conservative. I don't even want to say, I want to say I am below that line. Or in that line, right? It's fine. I want to give a space for more Dharmata candidate for any person that wants a Dharmata candidate. But basically, yeah, you have to be in the line if you want to do you do the full scan. You know, it's a bit time consuming because a little bit, it's on channel, but not a big deal. You can do micro meg or whatever you want. Huh? That. Right. 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 This coupling doesn't change. I mean, the change from 5 to 10 GB is basically very minimal. Then it's basically that coupling in that multi-TeV scale. It's the same. It's very minimal, the change. In principle, you could make a little bit of correction. No, no, look at that. Think about this term, right? I try to show you. You gauge lepton number, total lepton number, you break, okay? Right, here you go. And this guy get a BEF, there is always a C2 protecting for all the new fermions. And then the Lilas one is a neutral guy and it's a stable, it's a dramatic candidate. Then there is a C2 symmetry after symmetry breaking that you didn't put there by hand, was there after symmetry breaking, right? Right, right. For the new guys, yeah. Yeah, absolutely. No, no. You can make that, you can do what he tried to say. You try to write a high dimension operator. The dark matter has selector number 3 half here. It's no way you will find high dimension operator. Also, well, no, but he's worrying. He's worrying about the fact he's writing. No, he has a point. We can discuss later, but he just want to say, can I write any high dimension operator that will spoil? The question is no, because this guy has 3 half. If you use Lorentz invariance and the fact the lepton numbers, you know, you can try. You don't never get a high dimension operator, but it's a good point. Because you know, people write models where they don't check the dimension of 5 operator is killing you. Okay, let's discuss later. Both of you are totally in agreement, I think. Anyway, you do the job for Rayleigh density, better you do the check direct detection. I will not discuss that. But you know, here, in this case, the CL doesn't talk to quarks. Then you can do kinetic mixing, but this is not predicted. Then the Higgs is mediating that. The message here is that the mixing angle between the two Higgses, if it's below, let's say 10 to the minus 2, you satisfy all the bounds. And it's not a crazy number because this is a standard Higgs and the new guy that is at the Camille, the TeV scale. Now, it's something that you will like if you like actions, because I told you there is a pseudo Boston boson here, J, that he behaved like the Myron. The Myron is a guy that was predicted, I say Roncadell, meaning 82, where they were Max Planck student and postdoc. That basically it's a pseudo Boston boson coupled to neutrinos. We call this a Myron. Yeah, but it's broken, right? But the point is that depends what is the global symmetry of the scalar potential, right? Because S give mass to the C prime, but I have for the seesaw mechanism, I have this scalar field is here when lepton number 2. This guy has lepton number 3. Okay? And right, you have the two scalar if you want the seesaw mechanism, right? I want the seesaw mechanism. Okay? It's a scale, and then a combination of the imaginary part of these guys is also the ghost and balls that get mass by dimension 5 operator. Then this guy also can decay to photons at one loop, where inside the loop you have the new guys needed for anomaly cancellation, the new fermions. Then this guy behaves like an axion that decay to photons as well, but also decay to neutrino. Of course, you have to check, depends on the mass, you will decay to photons mainly or to neutrino. Every time that you have that, you have to check the lifetime, because cosmology doesn't care how, if you like your model or not. Then Big Bang nucleosynthesis will tell you, wait a second, what is the lifetime of this guy? This guy can live more than a second. And if you check all the bounds, the two lines are, depends a little bit of the mass of the new fermions inside the loop, a little bit. You find that if this guy is about 1 GeV or something like that, you're in agreement with all the Big Bang nucleosynthesis bound. What happened, this guy is making a mess for you, okay? In this regime, you decay mainly to photons, and this is, at least for people working heavy action stuff, this is actually what is happening. And this is actually interesting, because you are getting even extra degree of freedom that behave like the action sometimes. And you could use maybe all these things people think about the action to constrain this model more. Now, again, let me go back before I keep going. I don't want you to get, I don't want to make a mistake to go too fast. Basically, the first point I want to make is that if you want to write down a simple theory for neutrino masses, the simplest thing you can do, somehow this was overlooked in the community, it's hard to imagine. You try, instead of doing granified theory, whatever, everything is super high scale, you just try to gauge lepton number, total lepton number. You need to cancel these anomalies. The first model that I show you was no minimum, was just try to mimic what we have in the standard model. There, I show you, you get a dark matter candidate, you do the usual phenomenology, and you get this interesting property of the Myron. It's like an action sometimes. Has nothing to do with the strong CP problem. It's just this guy can give you, has a coupling to photons at one loop. That can be actually large because the symmetry-breaking scale is TeV, it's no Pechek-Wing scale. Again, doesn't matter what solution I show you today, you will get always a dark matter candidate. I mean, of course, you can do a crazy stuff where you destroy everything. I am talking, you only can make clear statement in simplest model or minimum model, okay? It's like the standard model. It works when only one Higgs doublet. Of course, you can put 25, but nobody asks you for that. When one is working, you can make clear statement about something like that, right? Now, this year I was lucky enough to find what I call the super minimal thing. It's how many fermions you have to add to cancel all the anomalies, actually, even for baryon number, but I will know, we'll talk later about that. And I was happy to see that apart from the right-hand neutrinos I want for the seesaw mechanism, only 4 fermions are needed to cancel all the anomalies. Okay, and this is what I call the minimal. The other was a bit more complicated, but it was very similar to the standard model. Again, what do? Is you forget about everything, go back again, check all the anomalies. That anomaly, SO2 left square U1L, tell you that there is no way out. You need some SO2 degree of freedoms, okay? There is no way out. Then you find that having only these 4 guys, okay? You can, since in this case, I don't care about color because I'm talking about leptons. Only having these 2 guys, 4 guys, you can cancel all the anomalies. The lepton number is 3, 4 for this guy. But look at this guy, it's always there. There is always a guy 1, 0, whatever lepton number, it's always there in any of the solution that we found for a long time. And anybody tried to find. Again, as I said, even in one of my papers, we found the solution with only 3 fields. But the point is that if you predict fractional things with fractional electric charge that cannot decay back to dark matter, that's not model, don't do this because you don't want to spoil cosmology and do weird stuff. And I'm talking about minimum model where everything can be done and you don't make a mess in cosmology, okay? Only 4 representations are possible, okay? And I will discuss this a bit more. And of course, you need something with SO2. If you are a fan of supersymmetry like me, this guy is like the winner, okay? Just with some extra quantum number. Yeah, it's automatic. No, because for example, let me give you a feeling. Try to cancel two square you want else, right? You can put whatever you want there. But that guy, that anomaly is 3/2. Then always you will. Oh, the mix is easy. The mixing and the qubits are tricky because you need the qubits and the linear are pretty hard to cancel, but it not so hard when you have the same degree of left and right handed, in this philosophy. But the SO2 square you want is equal to 3/2. This will always give you a fractional stuff. 3/2 is a weird number, right? Oh, that's this is yeah, but that's is easy because for example, this guy doesn't have any aperture, right? Then these guys are basically canceled then because you have some they're Berthold-like, and you just change the sign, you will be able to do that. Oh, no, wait. Any abelian symmetry, the normalization is no, but this doesn't change anything in the anomaly, right? All of them will have the same type of normalization, excluding the U1 cube. But again, I just put just the same normalization for everybody, then I do the anomaly cancellation. Well, okay, let me fix this comment. It's very simple. The standard model leptons tell you what to do. You say the normalization is in such way that they have lepton number 1. You're done. Yes, this convention. In that convention, these are the numbers. Let's talk later. Sorry about that. Okay, and then I don't want to drive you crazy to show you too many models, okay? Then what I want to give you, at least in this part of the talk, a well-defined message. Neutrinos are massive. There is no way that you can avoid that problem. You think about that, in this super simple way, you get the dark matter candidate. As far as we found for a while, doesn't matter which model you choose, typically you get a dark matter candidate. The CISO scale has to be low, and the phenomenology is actually consistent with cosmology. And this is typically the case. By the way, for us, this was a totally accident because we didn't even think about any of things in the beginning. I just tried to rewrite things in a different way. Later, I will tell you how we even start thinking about that. But neutrinos tell you what to do. You follow them, and it's the simplest symmetry. People get very confused when B minus L for historical reasons. B minus L doesn't tell you anything even because it depends so much how it's broken. Here, you are forced to break in 3 units because you have to give mass to these new guys. There is no choice, and everything follows from there. And the second part of the talk that looks different, but it's actually very similar, is actually how we started the thinking about this problem. Baryon number is also there in the standard model. Basically, you could say baryon number and total letter numbers are the simplest symmetries that we have in the standard model. And people often don't pay so much attention to this because they think everything is high scale and everything is okay. However, all these high scale theories, you break these symmetries explicitly when you unify matter. But nobody questions so much how you can gauge this symmetry and understand the symmetry breaking, okay? The reason why people probably never thought about that is proton decay, because typically if you break baryon number, good luck, because the proton decay bounds are so hard that you have to go to the Gauss scale, typically. Okay? And this is the second part of my talk, is that if you do the same exercise, you go back to the standard model, you forget any extension of the standard model that has been written, you say, very simple thing. Can I gauge baryon number? Again, it's also broken by SO2 instantons. You have to cancel the anomaly. And however, it's not clear that this is possible, because if for any reason you get proton decay, uh, everything has to be high scale. And probably, you know, and actually I remember when I started talking about that, people didn't believe me this was even possible. Anyway, if you're a young person, don't listen too much to people. Just keep going. That's by the way, I put a question here for the young people. I don't want to give a talk about that. You can ask me, please. How that works? Baryon number is different from, in many sense. These are the anomalies, and as I said, it's not a surprise you have the SO2 anomaly there. Again, Abraham Pais was a professor at the Institute for Advanced Study in Princeton. A guy has to actually escape from Holland, but he was Jewish. He was there, the guy who wrote a beautiful book about Einstein. He was the only person that wrote a tiny letter where he say, "Oh, maybe we should think about baryon number as a local symmetry." That paper was ignored in the community totally. Nobody even paying attention to that. This tell you often people follow fashion. You have to be careful, because fashion maybe is not the best thing to do. But he didn't write any model or anything like that, but he has a footnote that he said the Schwinger talk about that in some, but he never published that. And he was the only one who started to think about, oh, maybe I can have a local symmetry. These are the anomaly. As I said, you can look for many solutions. I will not tell you all the solutions, but I will tell you what the minimum model is. And the minimum model is like that. I put color now because the quarks, they have color. These guys, again, this is minimal speculation. I want to put the minimum number of degrees of freedoms, okay? These guys can have baryon number in the same way as before I mentioned, and you can cancel all the anomaly. There is nothing more than this, okay? Then if you want to give mass to them, it's actually, these are the only terms that are allowed, okay? These are the only terms that are allowed, okay? Notice that this guy always will be Majorana. This is a good thing about minimum model. They can make even better prediction. In the previous model, it could be Dirac or Majorana Darmada. It's actually Majorana. And the Higgs has baryon number 3/2, okay? The only extra thing that you have to do here is that you don't want to make mess in cosmology. This means that the new fermions that have charge -1, they have to decay to dark matter and the standard model, okay? Then you can accommodate that using the extra Higgs there. But there is nothing that more than you have to do. There is not even any other Yukawa term that is allowed, okay? Then they actually, as I said, this guy, L, is not the only dark matter candidate there, but I try to talk to him because he's the guy he's showing up in every solution that we found. Then I try to pay attention more to the Chi L. He's a neutral guy with this baryon number 3, 4, and 3/2. And then one interesting thing here is that you can break the symmetry and the proton is stable at any level of perturbation theory. There is no way you can write something that the proton is stable. This model is also a theory for proton stability, because actually, this is one of the reasons I took serious the proton, because in any unified theory or anything, proton will decay and will tell you the symmetry-breaking scale in your theory has to be super big. And I got into this game because I actually was not even thinking about that. I just wanted to see if I could get low scale unification. The only experimental constraint that doesn't allow you is proton instability. But if you have a theory where what I am talking about is possible and the proton is stable, the symmetry breaking scale can be low. Now, how low? The collider people will tell us. But the nice thing is the fact that I have a dark matter candidate, they have an upper bound symmetry breaking scale as before. Let's see. Then, if you want to do series phenomenology, you have to check carefully. You have the gauge boson there that talk mainly to quarks and the new fermions. You have the standard model like Higgs. There are two Higgses that are mixed. The phi is a complex scalar field. I'm not giving even a BEF. We can talk about that. You have two Majorana fermion. Your Wino, if you are a SUSY guy, the neutral part of your Wino is there. Then if you like Wino dark matter, welcome to do that. But I want to talk about Chi because it's the, let's say, it's the guy that's showing up in every model. And then you have two 4-component guys with negative charge. And if you are an expert on minimal dark matter, remember there is a one loop correction split in the masses. Huh? Now, how low the symmetry breaking scale can be? Well, again, the C prime here has coupling only to at 3 level, only coupling to the quarks and to the rest of the new fermions. Okay. Then, if you like collider physics, you will love this plot because look at what is happening here. This is the mass of the C prime, and this is the gauge coupling. This guy can be pretty low here, the mass, very low, in agreement with every collider bound that has been reported, and actually we did in this paper. This is a gauge coupling. Often you read papers that they say, oh, I can have a light C prime, but you check the gauge coupling is 10 to the minus 7. Then, I mean, I don't know. You don't see that. That's the fact that the mass is smaller doesn't help you so much. Again, this is the only gauge theory that I know where the symmetry breaking scale can be pretty close to the Letroux scale without assuming a small gauge coupling that is in agreement with collider. Okay? Very low scale. Okay? This means that maybe you can actually find that. Okay? I will show you later. Basically, what happens is, this is from our paper, you see all the experimental bounds. I know, again, this is a mixed community here. I try to jump a little bit in a few things because, I think it's the proper thing to do. This line, what happens is all these bounds, they don't assume that the C prime can go to dark matter, invisible, right? But when you allow that possibility, you relax the bounds, right? That is the, right, the rest are like jets, and you put monophotons. In the low mass region, you have to do monophoton, monojet, together with the two jet. You have to do everything too. Right, but right, but this is actually very suppressed. Okay. Again, you allow the dark matter depends a lot on what the dark matter mass is. Okay, but the experimental bounds that you see there, they are just assuming the C prime decay to 2 jet. Okay, only that. But that's look at that. The guy can have a G1 in the standard was 0.3 and G2 0.6. You don't have to kill the theory. Again, talking about a light C prime when you are killing your theory when super small coupling doesn't help. No. Here is the C prime can be low. The gauge coupling can be pretty standard model like. No. Okay. Now, one thing that is surprising here in the theory is that the new Higgs there, I call this guy Cucuyo because I was born in Cuba. And, when I was a child, I went to the forest and see a lot of these guys in there. I actually, one day, somehow I got this idea. Oh my goodness, why Cucuyo? This is an inkset that during the night can illuminate so much the forest, but during the day, it doesn't emit any light. Okay, you understand why I call this a Cucuyo Higgs. What happens is that the mixing angle between the two Higgs cannot be large because direct detection. I am coming there. But this guy can decay to 2 photons in a huge brushing range. Okay, this is a Cucuyo and decay mainly to photons or illuminate. And here in this example, the dark matter is like 200 GeV. The guy goes totally dark, decayed. And of course, there is something in between when you open the WW threshold, you go mainly to the standard model type of channel. But at the below the WW threshold, you can decay to mainly to 2 photons because this coupling is generated by the new fermions. These new fermions get mass from the new Higgs, and this is like the Higgs with the top, right? It's a huge stuff coupling. There is not a coupling effect there. Even if you change the mass of the new guys a little bit, you get a huge coupling and can decay mainly to 2 photons. The branching ratio can be large, of course, when you are below the WW threshold. Okay? Then if you never heard about the Kikuyu Higgs, this is actually made up that. This is exciting for collider physics because you can have a Higgs, can be light, can decay mainly to photons. This is a little bit hard to get unless you play some gymnastics. Yeah, the only thing is that the mix between the standard model Higgs and this guy has to be smaller than, let's say, 10 to the minus 2 because direct detection. Okay? And there is no weird thing here. As I said, the dark matter, the main difference in the minimum model is that dark matter is always Majorana here. Because it's so minimal, you don't have, the only thing that you can generate for the neutral field is that you can only write Majorana masses. And as you guys were asking me for, after symmetry-breaking, there is a C2 protecting the dark matter candidate. Nothing by hand. Okay? You have to do the Rayleigh density again. This is way simpler than before because you will annihilate only to, let's say, to quarks through the C prime, to the Higgses, but mainly 2 channels that will dominate. 2 channels will dominate is basically this in the resonance, or this guy will dominate in the most generic region. Okay? This is what you get. This is the mass of the C prime and the dark matter mass. These are the 2, if you are inside here, you have a resonance. This is not very generic. But if you are here, you satisfy the cosmological bounds. Michele, right? Right? This is the bound that we were talking about. Also, the fact that dark matter is getting mass from the same symmetry-breaking scale. Unless you break perturbativity, you don't want to be there. This here is ruled out by direct detection. Then you can live here without any problem. And the most important collider bounds here are from TT bar, because you produce CV, the guy decay to TT bar, and the bounds are very good. When you are in the low mass region, the QCD background is so hard that the bounds are very, very weak. And again, the nice thing about this is this is a simple theory where you have a spontaneous baryon number breaking at the low scale predicting a dark matter candidate, and cosmology tell you where you have to live. You can increase a little bit the gauge coupling. I just try to want to give you a feeling how much the scale can go up, you know, like below 20, below unification. Okay. Here, again, this is Majorana. The scattering cross section through the CV is velocity suppressed. So you can live at the low scale without rolling with direct detection. Still, you have the Higgs. That's why the mixing cannot be all in one. But you can, you know, if you are below 10 to the minus 2, you can do okay with the direct detection. Nothing peculiar. Okay. One thing that I find fascinating about field theory is the last thing that I promised to tell you. How much time I have? Maybe 0. 0. Oh wow. Yeah, this I went too slow. Okay, 0 minutes. Okay, then I think if it's 0 minutes, I only want to tell you something very quick, and I will jump to the conclusion because I hate to go to a seminar myself and be there, and the speaker doesn't stop. Maybe you heard about Nimar and Hamed. You know? Because start a little bit later. Okay, 5 minutes. Oh, no, it's not your fault. Okay, one thing that I personally find super interesting in dark matter phenomenology is the possibility to have gamma lines from dark matter annihilation in the galaxy. And the reason is because, you know, the mechanisms, there are like millions of mechanisms for dark matter Rayleigh density. Direct detection depends a lot of many properties. Gamma lines is very interesting because if one day we are able to see this gamma line from different places in the galaxy, and these are a gamma line way far away from any atomic transition, you can really say, oh, looks like this is could come from a place in the galaxy that is sitting around. Then if you're lucky to have a theory which predict, let's say, a gamma line, and the continuous spectrum doesn't bother you, we call this, you can see the visibility of the dark matter is quite clear. You can have many processes, even in your theory, that could spoil the visibility of the gamma line. Then if you are able to get the gamma line, let's say when the energy equal to the dark matter mass, let's say TeV or multi-TeV, you know, most of the people don't check that, compute gamma lines, but you have to make sure that even in your whole theory, there are processes that could actually spoil the visibility of the gamma line or the transition from the continuum to the gamma line. I will not bother you because it's too late. But basically, these are quantum mechanical process that if you have no anomaly free theory, good luck. But you know, here everything is under control. I will show you this plot. Basically, you can compute the annihilation, the dark matter, let's say to a gamma and a Z. We know the Z mass. And every point here satisfy the 0.12 Rayleigh density. Means that, you know, you're assuming that you are doing the job for the 0.12 Rayleigh density. This guy is sitting in the galaxy. And you compute the annihilation cross-section of one loop for the Z gamma. And you change the dark matter mass. I want the Kikuyu Higgs to be light. This guy gave me Sommerfeld enhancement because it's a Yukawa, right? And this is really nice. And it means the cross-section can be pretty big in agreement with everything. And Hess is killing already part of the parameter space. I am able to get the dashed line is the CTA projection, which actually could touch most of the parameter space. Again, every point here satisfies the Rayleigh density. I don't have to worry about direct detection. This is a heavy guy, there is no problem. But the amazing thing is that in this theory, you can have a huge cross-section for the gamma lines. And something more that I want to show you, you know, now you have to check all the process generating photons to make sure that you don't make a mess. You compute the total flux of photons. You see, you can have a gamma line like this, or this gamma line. For a heavy guy, the C is almost massless for a TeV guy, but the energy is a little bit different. And there are processes like final state radiation, or this guy that came from the Higgs decay, that in principle could spoil the visibility of the gamma line. But you can see the other processes never go up, and you will get a nice gamma line, and you can actually see that the flux can be actually large enough and be close to the CTA bound. Repeat again. The final state radiation can get very, very close. I could show you. Well, the astrophysical background is important, but I always think if you see that from different places in the galaxy, I don't see, you can kill that. Well, okay, that's a different story if you believe that. Okay, this is a different example. But before I finish, because I am the multi-TeV is a very heavy guy. It's not Dan Hopper stuff. No, but this is a heavy guy. The winner we can actually discuss. It's a little bit different. Okay, this is because the gauge interactions, but for the doublets and so. Okay, let me finish because I don't want to keep these guys here, but I will go. Before I finish, I wanted to show you. I told you that in this case, the symmetry-breaking scale can be very low in agreement with collider bonds. This means that at high luminosity LHC, you can produce the Higgs together with the C prime. The Higgs can decay with a large fraction relation to photons, if you slide. And the CV can decay, let's say, to two top quarks. And if you compute the cross section, you can see that high luminosity LHC could do actually pretty well. That's how I got involved with the experimental from UCLA, John Butterwood, because he really asked me, let's try to check how well we can do. And we actually, during this day, we are working on this, and I want to give you a feeling. Still, the LEC could actually see something like that, okay? Because it's large enough, okay? And as I promised, I finished. Sorry if I was a bit slow, but I had 5 minutes. I want to give you a feeling in the beginning is that the all ideas of the neutrino dark matter and actions are good. And the reason that they were and they are good is because you start thinking about a problem, and as a bonus, you get the dark matter candidate. Here is happening the same. Here is, in some sense, at least the first part is way more pragmatic because we have to think about neutrino mass. Lepton number is a simple symmetry. And the only thing that I am asking, let's try to write a theory where you have a spontaneous breaking of lepton number and you get a dark matter candidate. The second part of the talk is a bit, maybe for you, a little bit more speculative, but baryon number is a pretty important symmetry for baryogenesis and for anything. And it's good to understand if you can actually write a theory consistent with proton decay and any collider bounds at the low scale. And basically, that is what I try to mention. As a bonus in this theory, you get a dark matter candidate. The symmetry-breaking scale has to be low. The gamma line, if you are willing if you want to discuss a little bit, we can discuss more about that. This is beautiful here is that the gamma line predictions are very close to the CTA bounds. And as I said, the most interesting part for me is that there is a hope to test these ideas at collider because everything is happening at the low scale. And this is actually the message that I wanted to give today. I believe in the field, we got too much involved on simplify things, which are okay to understand the phenomenology, but I have a feeling we have to go back to the old fashioned to write theory for something. Write a theory for something and see what you get. And here you see, you get a bonus. And I think it's important. Thank you. I was waiting for that. That's a good. There are different possibilities. One is the standard way that you have more degree of freedom on the low scale, let's say, and you can change the electroweak phase transition and do like a normal electroweak baryogenesis modifying, right? It's one possibility, right? It's broken. You break a TeV scale, let's say, no? And then the electroweak phase transition can change because you have new Higgses, you can, this is one way of the story. The other way that I personally did together with Mark and other people, that you could have a scenario for asymmetry dark matter. But knowing this minimum model, we actually implemented that because you can if you have a model, it's not the minimum one. You can write coupling between the standard model matter and there is a symmetry. You put a chemical potential for everybody, and we actually wrote papers about that. This is actually kind of the best framework to do a symmetry dark matter because there is a symmetry tell you what to do, and you can do. And actually, we did that but then not in the minimum model. In the minimum model, you had to do basically change the phase transition with the degree of freedom. But what the nice thing about that, think about that. We say, oh, we have a breaking of baryon number, but we never have control what is happening in the baryon number. Here you have control. There is a symmetry, it's broken here. You understand what is happening. It's not that maybe you have like 20,000 other mechanisms. No, baryon number tell you everything should happen below this scale. Whatever mechanism you want to implement. And by the way, you didn't ask me about unification. I should tell you. For anybody that works about unification, what happens is that in any unified theory, proton decays, and then good luck with that. Here, I was able to unify baryon number with QCD, and I can write alternative unified theory, but the proton is stable. then you could manage to have unification lower scales. That is it's like you look for a new way to have unification, but no other super high scale. Yeah, you have QCD and U1. I can write through. We have SO4 color, and the U1 variant is inside. And then I can able to unify the other groups. I had to go up, and for example, we are able to have something like there is a theory that is called tree unification. That is SO3 cube. This is not a full unify, no. But then we are able to using this idea to have a theory that is SO4 cube. Okay, that in principle you can put that in a sectional group. Okay. But again, the good thing is that doesn't matter what UV completion you are using, if you are able to get these minimum models inside, the proton is protected. Then you can unify a lower scale because there is some proton decay. That is actually how I got into this game. The neutrino stuff became way later. It's like reverse the whole thing. Any question from the students? Oh, it's true that you're okay. Only one student. Sorry. Sorry about my Italian. If you don't feel comfortable speaking English, you can ask me in Italian. I say my Italian is good enough to answer. Not sure about that, but I can try. Thank you.